Okay, welcome back to our videos on rolling. Now we're going to finally take a look at an example of rolling and see how this new knowledge affects some situations that we've considered before. What we're going to take a look at is an object rolling down a ramp. And actually first, we're not going to take a look at an object rolling down a ramp, we're going to look at our old case of something sliding down a ramp. So here is our ramp. We're going to put a nice circular object up there to roll down it. And that object is going to be of radius r. And again, what we're looking for is a sphere, either sliding or rolling down a ramp, and we're going to compare those two situations. They are not the same thing. Sliding and rolling are totally different. One of the things that we will need to know for this is the moment of inertia, or rotational inertia, for a sphere is 2/5 mr squared. First thing we're going to do is take a look at the case for sliding. For objects that slide down ramps, this is what we first studied when we first started talking about ramps in physics. We have the object of mass m. We're going to tilt our axis, x, y. There's a normal force perpendicular to the ramp surface, Fn. There's a force of gravity straight down, Fg. And, let's see here. Let's make the assumption that this is, that there is no friction on the object. Yeah, let's go with that. If that's the case, then we break this up into components. Here's theta, Fg cosine theta, and Fg sine theta. Okay. The net force equations will look like this. F net x equals Fg sine theta equals max. This turns into mg sine theta equals max. I cancel the m's. I'm left with ax equals g sine theta, without even doing the net force in the y direction, but I'll provide that anyways. Fn minus Fg cosine theta equals may. That's 0. Fn equals mg cosine of theta. But the key result that we've gotten before for an object sliding down a ramp is that the acceleration is based only on the acceleration due to gravity and the angle of the ramp. For an object that rolls down a ramp, things are a little different. Why would an object roll down a ramp? Well, it actually turns out that objects do not roll unless there is friction. Friction is necessary to provide the torque to cause the object to have an angular acceleration and start to roll in the first place. This object that slides down the ramp, it could spin while it slides down, but the rate of spinning is not going to change. You can start this object spinning, but that wouldn't be called rolling. Rolling is very specific, okay? Rolling involves no motion between the point of contact on the surface and the object that is doing the rolling. So, in a case where there's rolling, it would roll because of the force of friction. If there's no friction, just like over here, it slides. As a matter of fact, if the friction isn't strong enough, it also will slide, but maybe with a little bit of rolling thrown in. Since it's going to be rolling, and this is going to be rotating, and since it's going to be rotating as it moves down, we can assume that it picks up some angular velocity, it keeps increasing. We really need a free body diagram that is not just a dot, but that is an actual circle representing the sphere. Okay, we're still going to have our same axis, And since the sphere is rolling down this way, we're going to say that, again, the clockwise direction is positive. Now, the forces on our sphere. There is a normal force from the incline, from the ramp, points up in this direction. There's a force of gravity acting from the center of the mass of the sphere, straight down. And there's a force of friction parallel to the ramp surface, and that actually acts backwards. Now, the reason that acts backwards is, imagine what would happen if the sphere were simply sliding down. The relative motion between the sphere and the surface would be sliding this way along the surface. The force of friction from the surface on the sphere must act opposite that. It acts to stop the motion that would otherwise happen. Okay, so it acts from there. The other thing that I have to do is I have to break the force of gravity into components, just like before. Here's our angle. This, once again, is Fg cosine theta. This is Fg sine theta. The net force equations. In the x direction, we have Fg sine theta minus the force of friction equals max. Now, we don't necessarily know exactly what the force of friction is. We don't know if it's at a maximum. We don't know if the force of friction is at a maximum. It could be, okay? It could be at a maximum. If it were any bigger than that, if the force of gravity pulling it down were any bigger than that, and the force of friction was at its maximum, then we would get sliding. So we don't know if that force of friction is at a maximum value or not. If the force of gravity ends up being too big for the force of friction, what will happen is the object will start to slide. In other words, if the force of friction is too small. So we don't know if this is going to be equal to mu Fn. Okay, so we're not going to go there just yet. We can't make that substitution. We do know, however, in the y direction, the net force Fn minus Fg cosine theta equals may. Just like before, Fn equals mg cosine theta. So, if we are trying to compare the accelerations, the issue here is I don't know how big the force of friction is. However, we know that we're trying to induce rolling. So, what we're going to do here is we're going to do a net torque analysis. We haven't done that yet. The normal force acts from a spot, well, the axis of rotation is right in the middle. Okay, the axis of rotation, that's the spot about which the sphere rotates. The axis of rotation is right here. The normal force acts from a spot, but the line of action of that force passes right through the center. Okay? Another way of saying that is that the force is in this direction, and the direction and the r vector from the axis of rotation out to here is anti-parallel to that, 180 degrees. There's no torque from the normal force. Likewise, because the force of gravity acts from the center of mass, which is where our axis of rotation is, there's no torque from the force of gravity either. The only torque exerted on this sphere is from the force of friction. So the net torque is equal to the torque from the force of friction. That's equal to I alpha, and that's a positive torque. The torque from the force of friction is going to be equal to R, the force of friction, times the force of friction, times sine theta. As you can see here, R is out in this direction, FF is perpendicular to that, so this must be 0. The moment of inertia for the sphere is 2/5 mr squared times alpha, which is the angular acceleration. R is just the radius of the sphere, so I'm going to drop that. I'm just going to have R times the force of friction equals 2/5 mr squared. And then that alpha, remember that the angular acceleration is related to the linear acceleration, which in this case would be ax, the acceleration down the ramp, divided by r. So I'm going to make that substitution. I'm going to call this ax divided by r. Look what happens to my r's. One set of r's cancels out over here, and I still have r on this side and r on this side. That will also cancel out. The force of friction must therefore be equal to 2/5 times max. In other words, the force of friction, that's the force of friction to allow this to roll, okay? Let me actually take a step back. By saying allowing it to roll, we're assuming this condition right here. This condition is the prerequisite for perfect rolling. The angular acceleration is equal to the linear acceleration divided by r. So since we're assuming rolling, we have to assume this. And if we're assuming rolling, we now know that the force of friction must be equal to 2/5 times m times ax. And remember where that 2/5 came from. It came from the sphere. It came from the moments of inertia of the sphere. That's where it originated. So different objects, like let's say if you had a hollow sphere, this is for a solid sphere, a hollow sphere with a different moment of inertia would have a different value here. A disk, a hoop, would have different values here. Since we now know what the force of friction is, we can plug that in up here to find the acceleration. Rearranging, I have mg sine theta minus 2/5 max equals max. I add 2/5, well, first of all, I can cancel out all my m's. I add 2/5 ax to the other side. I get g sine theta equals 7/5 ax. And therefore, the linear acceleration down the ramp must be 5/7 g sine theta. Compare this to the acceleration in the case of sliding. It's less. And I think that makes sense. Less than, let me make sure we can read all this. Less than for sliding with no friction. So, the object must have a slower speed at the bottom. And this is consistent with what we talked about in one of the previous videos. This agrees with how rolling objects don't tend to obtain as high of speeds as sliding objects. And that's kind of interesting. Now, we talked a little bit about how rolling does require friction. And it requires a certain amount of friction. Matter of fact, if there is not this certain amount of friction met, then the object will at least slide some. So we can actually go back and find what that minimum amount of friction is. And it has to do with using this acceleration and going back and solving for FF. So if looking for mu min to allow rolling, and again, otherwise slipping would occur. It would look something like this. Let's take our equation from up here. Fg sine theta equals, minus Ff equals max mg sine theta minus mu fn equals m, and we're going to take the acceleration that we just found, 5/7 g sine theta. That's the acceleration of an object if it is rolling, or for this particular solid sphere that's rolling down the ramp. 5/7 g sine theta. I'm going to plug in my value for Fn, which is mg cosine theta. So I have mg sine theta minus mu mg cosine theta equals 5/7 mg sine theta. Notice that every term has an mg in it. Cancel all those out. I'm solving for mu, so I'm going to subtract sine theta from the other side. I end up with minus mu cosine theta equals minus 2/7 sine theta. I have negatives on both sides. Those cancel out. I divide both sides by cosine. I end up with a minimum coefficient to allow rolling to happen of 2/7 tan theta. That is the minimum coefficient of friction to allow rolling to happen. Anything greater than that, fine. Rolling happens, nothing changes with the acceleration. Anything less than that, and slipping occurs. Now, last but not least, well actually before I go to that, this is a general overview of rolling. I know I threw a lot at you right there, but a lot of the problems for rolling are very similar to this, okay? You're trying to figure out how, usually you're trying to figure out the angular acceleration or the linear acceleration of the object down the ramp, so you can do things like figure out how much time it takes to get down the ramp, how fast it's moving when it gets down the ramp, and stuff like that. What we want to do now is compare how different moments of inertia compare in energy and speed. Remember that the formula for moments of inertia is I equals B, which is a positive coefficient, mr squared, where B is a positive constant that is dependent on shape. Okay, so remember that our equation in the x direction, our net force equation in the x direction, last time was Fg, I'm just kind of skipping from up here, Fg sine theta minus Ff equals max. If I wanted to solve for the force of friction, I would get this. Force of friction equals mg sine theta minus max. Now, I'm going to put that into my net torque equation. Remember that that was the torque from the force of friction equals I alpha. And again, remember that alpha equals the acceleration, the linear acceleration, divided by r. So I get Rf, force of friction, sine theta f, remember that that's 0, equals, let's see, I is bmr squared times alpha, which is ax over r. One set of r's cancels out. I now have r, force of friction is mg. Oh dear, I'm writing way below this. Sorry about that. Mg sine theta minus max equals bmr ax. I have m in every single term, so I'm going to cancel that out. And I have an r on both sides in every term. Those are going to cancel. I'm left with this. G sine theta minus ax equals b times ax. I bring my ax over to the other side and I pull it out. I end up with this. G sine theta equals ax 1 plus b. I'm left with the acceleration of the object as it rolls down the ramp, no matter what it is equal to g sine theta divided by 1 plus b. Remember that b must be a positive constant. So if b is a positive constant, any of these objects as they rotate, as they roll down the incline, b is going to be positive 1. That's going to be greater than, well, 1 plus something that's positive is going to be greater than 1. We're going to be dividing g sine theta, the acceleration for sliding, by a bigger by a number greater than 1. That's going to reduce the acceleration. So, because b is down here, if there is a bigger b, that leads to a bigger moment of inertia, which leads to a lower acceleration. And you can think from your kinematics equations, if the acceleration is lower, that leads to less speed. And from 1/2 mv squared, that leads to less translational kinetic energy. Okay? And that is why objects with greater moments of inertia have less energy, move slower basically down the ramp. They do not get to the end of the ramp as quickly. They do not get to the end of the ramp as fast. All right, so that's a lot on rolling. Like I said, a lot of the problems start pretty much the same way. Your job is to be able to understand why an object rolls based on the forces and torques that act on it. We'll do some definite practice with that. It's a little tricky, but if you have any questions, always feel free to contact me. All right, bye.